In the last lecture, we were looking at mass transfer from a particle using dimensional analysis to express the transfer rate as a function of dimensionless groups. First things, I told you that the mass transfer rate is an extensive quantity. So, so correlations are not written usually for extensive quantities, but rather for intensive quantities. And in this case, the intensive quantity corresponding to the mass transfer rate would be the average flux, the mass transported per unit area per unit time. The total mass transported would depend upon the diameter of the particle or the surface area of the particle, for example, and therefore, we write a correlation for an intensive quantity, the average flux, which is the mass transported per unit area of the surface per unit time. And once I have determined this average flux, I can just multiply this by the surface area of the particle to get the total mass transported per unit time. Okay. So, we write correlations usually for the average flux, and that depends, the driving force for this mass transport is the difference in concentration between the surface of the particle and the fluid far from the particle. That is delta C is equal to Cs minus C infinity. One of the mechanisms of transport is diffusion, and that will depend upon the rate of transport will of course depend upon the diffusion coefficient and the diameter of the particle. And then there is also transport due to convection, due to fluid flow around the particle, and therefore, the velocity of the particle relative to the fluid V as well as the fluid properties, the density and the viscosity are also important significant parameters. So, therefore, we have 1 dependent and 6 independent dimensional parameters, 3 dimensions, and you would expect 4 dimensionless groups. However, we made a simplification, which is to say that the solute concentration does not affect the fluid properties, okay, to say that the solute concentration does not affect the fluid properties. That means that the mass being transported is only of the solute. That can be considered a different dimension than the fluid density, which is the total mass per unit volume. With that simplification, there is now 4 dimensions and therefore 3 dimensionless groups, one of which is dependent and the other 2 are independent. The dependent dimensionless group is a dimensionless flux, and that dimensionless flux is obtained by scaling the average flux with quantities that determine the diffusive transport. I told you that you can get this relationship just by looking at Fick's law for diffusion. You could of course write it as in this manner and calculate the coefficients alpha, beta, gamma, etc. But a simpler way to do it is to just refer to Fick's law of diffusion. Fick's law of diffusion relates the local flux to the local diffusion coefficient, the change in concentration and the distance traveled, or the thickness of the slab. So, that is a local relationship. It does not apply for the entire system, it applies only locally at each point. Nevertheless, the right and the left sides of Fick's law have the same dimensions. So, I could as well scale the average flux by a term that has the same dimension as the right side of Fick's law, and that gives me this dimensionless group, the Sherwood number. Independent dimensionless groups, we have already seen the Reynolds number, which is the ratio of fluid inertia and fluid viscosity. There was a second dimensionless group that we obtained, the Peclet number, which is V d by the diffusion coefficient. It is the ratio of mass convection and mass diffusion. Therefore, the Sherwood number has to be a function of the Reynolds number and the Peclet number. Low Peclet number, convection is very small compared to diffusion. You can neglect convection or the fluid velocity altogether, and in that case the Sherwood number just becomes equal to a constant. What that value of the constant is, we have to determine by a more detailed calculation, turns out to be equal to 2 for a spherical particle. Becquerel number large compared to 1. Okay. Even though convection can transport fluid, transport solute along the fluid flow streamlines, across the particle there is no fluid flow. Okay. The particle has a rigid surface and it is not penetrable to the fluid. Therefore, there is no velocity perpendicular to the surface. Mass transport to the particle has to ultimately occur perpendicular to the surface. Okay. Mass transport along the surface cannot change the mass within the particle. Okay. Therefore, mass transport ultimately has to take place perpendicular to the surface, and that can take place only due to diffusion. Therefore, even when the Becquerel number is large, we cannot neglect diffusion. Diffusion does play an important role in mass transport. Okay. And I discussed the extension of this to a drying particle. Okay. So, let me go on to the next problem, and that is heat transfer in a heat exchanger. Okay. Typically, in a shell and tube heat exchanger, for example, okay, you will have a pipe okay. This is usually referred to as the tube side. So, you have fluid coming in and fluid going out, and then you have, okay, for example, you could have hot fluid coming into the tube side and cold fluid on the shell side, and therefore, the temperature of the hot fluid decreases due to contacting with the cold fluid, okay, as it goes through. Okay. So, of course, the heat transfer rate will depend upon both the conduction across the pipe wall, conduction within the fluid on the shell and the tube side, okay, and convection, that is fluid transport of fluid along the pipe, okay, which is driven by a pressure drop across the pipe, okay, as well as transport of fluid on the shell side. Okay. So, these are all the factors that will affect the rate of transport of heat across the heat exchanger. Okay. Once again, instead of expressing the transport rates as a transport rate per unit time, which is an extensive quantity, it depends upon the surface area of the shell and the tube. We will express it in terms of an intensive quantity, which is the average flux, Q average, which is equal to the heat transferred per unit area per unit time across the surface, okay, of the tube, okay, across which heat transfer is taking place. Okay. So, the heat transfer is taking place across the tube, and we express this in terms of the heat transfer rate, which is the energy transported per unit area per unit time. So, that is the heat transfer rate. Okay. The dependent quantity, what we want to find out. Okay. So, therefore, the dependent quantity, so let me just write that again. Okay. Okay. Average heat flux Q average, okay, energy per unit area per unit time. Okay. Note that energy has dimensions of mass, length square T power minus 2. Mass, length square T power minus 2 is the force into distance divided by area into time. Okay. So, this has dimensions of m t power minus 3. Okay. So, this can depend upon a number of independent quantities. Okay. Okay. One is of course the diameter d with dimension L, the length L with dimension L. Okay. So, these are just geometric parameters. Heat is transported because the fluid is flowing through, okay, convective transport. Okay. And that convective transport will depend upon the flow velocity and the fluid properties. Okay. So, the flow velocity is VAV with dimension LT inverse, the fluid properties density rho m L power minus 3, okay, viscosity okay. And then there are thermal properties. Okay. For heat conduction to take place, there has to be a temperature difference between the shell side and tube side. I will call this an average temperature difference between the shell side fluid and the tube side fluid, and the temperature difference has dimension theta. Okay. And then there are thermal properties. Okay. The thermal properties in this case are the conductivity, K, okay, that if you recall has dimensions of, okay, we had calculated this earlier, m L t power minus 3 theta inverse, and the specific heat Cp, which has dimensions of L square t power minus 2 theta inverse. Okay. So, now we have one dependent quantity and 1, 2, 3, 4, 5, 6, 7, 8 independent quantities, total of 9 quantities. Okay. 4 dimensions: mass, length, time and temperature. Therefore, there are 5 dimensionless groups, one of which is independent and the other 4 are dependent dimensionless groups. Okay. Now, as in the case of the mass transfer problem, we can make a simplification here by distinguishing between transfer of heat energy and transfer of mechanical energy. The fluid properties, density, viscosity, velocity, etc., are mechanical quantities, they are flow quantities. Okay. Whereas thermal quantities are the temperature difference, thermal conductivity, specific heat, heat flux. Okay. So, if we make a distinction between these two, if there is no interconversion between mechanical energy and heat energy, that is, if the mechanical energy is not converted to heat energy or vice versa, then we can consider mechanical and heat energy to be 2 different dimensions, okay, and have a different dimension h for the heat energy. Okay. Then we will get a total of 5 dimensions and only 4 dimensionless groups, okay, in this problem. So, let me write down what the dependent and independent quantities are once again. Okay. So, the dependent, okay, average heat flux, okay, Q average, which was m t power minus 3, okay, diameter d with dimension length, length L with dimension length, average fluid velocity, V average L T inverse, density rho m L power minus 3, viscosity mu m L inverse T inverse, and then the thermal quantities, specific heat, okay, Cp L square T power minus 2 theta inverse, and then the conductivity K m L T power minus 3 theta inverse, and finally the temperature difference with dimension theta. Okay, so, these were the quantities. Now, I want to make a distinction between thermal energy and the mechanical energy. The velocity, the density, the viscosity are all related to mechanical energy. Therefore, their dimensions remain as they are. The average heat flux is a thermal energy per unit area per unit time. Okay. If I use a dimension of thermal energy as H, the thermal energy per unit area per unit time has dimensions H L power minus 2 T inverse. Okay. Okay, so, I have introduced this additional dimension relating to the thermal energy. Okay. Similarly, specific heat, conductivity and temperature difference are all thermal quantities. Okay. So, specific heat, we know that the change in enthalpy is equal to m Cp delta T. Okay. Enthalpy has dimensions of H is equal to the mass dimension, the dimensions of Cp and the dimension of delta T, which is theta. Okay. Therefore, the dimension of Cp is going to be equal to H m inverse theta inverse. Okay. So, that is the dimension of specific heat in terms of these dimensionless parameters. Okay. Similarly, the thermal conductivity, we get it out of Fourier's law of heat conduction. Okay. Q is equal to minus K delta T by delta Z. Okay. For conduction, if you recall, across a slab, of distance delta Z in the Z direction, across which I have imposed a temperature difference delta T, okay, across the slab. Q is equal to H L power minus 2 T inverse. Okay, so, is equal to the dimension of K into theta divided by L. Okay. Therefore, thermal conductivity has dimensions of H L T inverse theta inverse. Okay. So, these are now the modified dimensions, where I have explicitly separated the thermal energy dimension from the mechanical energy dimension. Mechanical energy dimension is ml square T power minus 2 as usual, but I have separated out the thermal energy dimension in this case. So, now I have 5 dimensions H, M, L, T, theta, 9 groups, that means 4 dimensionless parameters. Okay. Dependent dimensionless group, okay. It should, okay, QAV, okay, and it can be scaled by the thermal conductivity or the specific heat, because both contain the mass dimension. I will scale it by the thermal conductivity. So, I will get K power alpha, delta T power beta and D power gamma. Okay. There is the Nusselt number. Of course, we can determine what is alpha, beta and gamma, but the simpler way to do it is to scale it by a quantity that has the same dimension as the right side of Fourier's law of heat conduction. Fourier's law of heat conduction applies only locally, it does not apply to the entire system. Nevertheless, the left and the right sides of Fourier's law of heat conduction have the same dimension. Fourier's law of heat conduction is Q is equal to minus K delta T by delta Z. Therefore, I can get a dimensionless group just by scaling, okay, the Fourier's law of heat conduction by the right side, by a quantity that has the same dimension as the right side, which will be QAV by K delta T by D. D is the length scale, the diameter of the pipe. Okay. So this is this is the dimension of this is the dimensionless flux, the scaled average flux, the dimensionless flux, the dependent parameter, that is the Nusselt number. Okay. What are the independent parameters? Okay, what are the independent parameters? An easy parameter is just the ratio of length scales, L by D. Both have length dimension, therefore, it is the ratio of length scales, L by D is an independent parameter. Okay. The second parameter is the Reynolds number, which we have already seen, rho V D by mu. The Reynolds number, so in this case it should be the average velocity. Okay, that is the Reynolds number. Okay. And there is a third dimensionless group that contains the specific heat and the thermal conductivity, because we have not yet scaled. The specific heat does not appear in any of these scalings so far. Okay. So, this number can be taken as specific heat to the first power, okay, and then to scale the specific heat I need the thermal conductivity, because that has the mass that has the heat energy dimension, H dimension, and I need to take either the viscosity or the density, because that has to because the specific heat has both the mass dimension and the temperature dimension. Okay. So, mu power beta, and to scale the length dimension I will have V power gamma, and the time dimension I will have V power gamma, and the length dimension I will have D power delta. Okay. Then you can go through the calculation and determine what this is. Okay. It turns out that there is an easier way to non-dimensionalize this, right. So, if I just take Cp by K, okay, Cp by K, okay, the dimension of this, okay, the dimension of Cp by K, okay, this Cp is going to be equal to H m inverse theta inverse, okay, by H L inverse H L T inverse theta inverse. Okay. You can see the H and the theta cancel out, and you get 1 over m L T inverse. Okay. This is precisely the same dimension as the viscosity. Okay. This is precisely the same dimension as the m L inverse T inverse. Okay. Okay. This is precisely the same the thermal conductivity this should be L inverse here. Okay. The thermal conductivity has an L inverse here. Okay. So, kindly correct that. So, there will be an L inverse here. Okay. So, this has precisely the same dimension as the viscosity. Okay. So, therefore, I can define this Prandtl number as viscosity divided by this, and that is Cp mu by K. Okay. Okay, so, those are the dimensionless groups, and therefore, the dimensional relation the relation between these dimensionless groups has to be of the form Nusselt number is equal to some function of the Reynolds number, Prandtl number, and L by D. Okay. Prandtl number, as we will see, will be the ratio of momentum diffusion and thermal diffusion. Okay. I can get an alternative relation for the dimensionless group as a Peclet number, which is equal to the Reynolds number times the Prandtl number. Okay. Expressed in this form, the dimensionless group is independent of the viscosity. Okay. So, you get rho V D by mu into Cp mu by K, okay, which is equal to rho V D Cp by K. This is only this is independent of the fluid viscosity. It depends only on the velocity and the thermal conductivity. And as we will see later, this is the ratio of convection and diffusion for heat. Okay. The earlier Peclet number that we had, V d by diffusion coefficient, that was a Peclet number ratio of convection and diffusion for mass. This is a ratio of convection and diffusion for heat. Okay. So, the relation between the dimensionless groups can be expressed in one of two forms. Nusselt number is equal to one function of Reynolds number, Peclet number and L by D. Okay. Okay. Either Reynolds number and Peclet number or Reynolds number and Prandtl number. Prandtl number is the ratio of diffusivities, Peclet number is the ratio of convection and diffusion. Okay. So, we have got these dimensionless groups by considering heat energy and mechanical energy as two different kinds of energies. Okay. And in that case, we have got a relation between the dependent dimensionless group, Nusselt number, and the independent dimensionless groups, the Reynolds number and the Prandtl number or the Peclet number and L by D. In that case, we had considered the so let me just calculate the thermal conductivity dimension again for you. Okay. So, Q is equal to minus is equal to the dimension of K, the dimension of delta T divided by length. Okay. So, therefore, H L power minus 2 T inverse is equal to the dimension of K theta by L, which means that the dimension of K is equal to H L inverse T inverse theta inverse. Okay. So, there is this factor of L inverse here, L inverse here, okay. And that is what has come in over here, okay. And that gives you the dimension of viscosity. Okay. So, we got the Nusselt number as a function of the Reynolds number, Prandtl number and this ratio L by D. Now, in the limit of low Peclet number, you would assume that diffusion is dominant. Okay. However, that regime is not actually of interest for a heat exchanger, okay, because if diffusion is dominant, right, we have a flow in a pipe. Okay. For a flow in a pipe, if diffusion is the dominant mechanism, okay, across the cross section, convection is not important. That means that the temperature will equalize across the entire length, entire cross section of the pipe before the fluid has moved very far, because diffusion is dominant. Diffusion transports heat in the cross stream direction, and where diffusion is dominant, the energy will equalize across the cross section of the pipe before the fluid has moved very far. And in that case, there is not much use in having a long pipe, because the temperature is equilibrated before the fluid has moved very far. Okay. So, the limit of low Peclet number is not actually a relevant limit in the heat exchanger. The relevant limit is only the high Peclet number limit, where the convection is dominant and where the fluid moves long distances before there is transport across the entire cross section of the pipe. So, correlations for heat transfer are usually written only for the high Peclet number limit, where convection is dominant and therefore, the heat transfer across the cross section of the pipe is much slower than convection along the length of the pipe. Note that, as usual, transport across the surface has to take place due to diffusion, because there is no flow perpendicular to the surface, and therefore, there is no transport across the surface by convection. So, transport along the pipe takes place due to convection, transport across the wall of the pipe takes place due to diffusion. And we are considering the limit of high Peclet number, where the convection is large compared to diffusion in the bulk of the pipe. but near the surface transport has to take place due to diffusion. I had made one approximation here, and that is there is no interconversion between heat energy and mechanical energy. I will come back and look a little closely at that approximation in the next lecture. Before I discuss, for this flow in a heat exchanger, you have to apply a pressure difference across the length of the pipe. So, how do we estimate how much the pressure difference is across the length of the pipe? That I will continue in the next lecture. That is a problem of momentum transfer. I will continue that in the next lecture.